So we have an opcode part. For example, we said add. We had discussed this example, if you remember. Yes or no?
Yes, ma'am.
Right. So you remember this example? Any problems in this?
No, ma'am.
Good. So we had eventually come down to a format for this, for instance, which looked something like this. So what will I do? I'll say add a, yes or no?
Yes,
Add
ma'am.
B. How will this operation be performed? Add B and STA X. Yes, students?
Yes, ma'am.
STM is store into AC. Right. So in all these kinds of instructions that you see here, what we are dealing with is generally an opcode, right? Which is, let's say, add in the first case, and the memory operand, which is A, right? Which is denoted by A. Okay. So this percolates down to a simple format of instruction, which is opcode followed by an address. That means what I'm trying to say is that each instruction will be of two parts. One will be the opcode. Opcode stands for, we have done this in the last class,
Operation code.
operation code, and address stands for the address where the memory variable is located. Last time we saw a in-depth example of this. I explained it with an in-depth example. Yes. Any problems up till here?
No, ma'am.
No, ma'am.
Now, there is another part which is called the mode part. What is this mode part used for? I will let you know later. Okay. But for the time being, now just to make our basics clear, let us suppose that we are only using one bit as the mode bit. That means the highest order bit. What is the highest order bit in an instruction? It is the leftmost bit. Okay, it is the leftmost bit in the instruction that is reserved for the mode bit. So obviously it can have two values, either a 0 or a 1. Is this clear?
Yes, ma'am.
Yes, ma'am.
Good. So let us leave the mode bit at this level. Let's leave its understanding at this level. Okay. And just work out the number of bits which are going to be required for each part of this basic instruction format that we have just seen. Okay. So what should be the total length of this instruction, students? If I have given that I have a main memory of the configuration, which is shown to you on the screen, that is 4096 cross 16, what should be the total length of instruction?
16 bits.
It should be 16 bits. Right. This is because we said that this configuration of main memory means that there are how many locations in this memory?
4096.
1096.
And each location is capable of storing how many bits?
16 bits.
16 bits.
This 16 bits is also sometimes referred to as the
Word
word length
length.
of this
Word length.
particular architecture. Yes or no?
Yes, ma'am.
So this is clear, right? Now, so the total number of bits is 16 bits. I had said that sometimes it can happen that one instruction could be longer than one word. But if this is the case, then it will be specifically mentioned to you. Okay. In case nothing is mentioned, then by default, one instruction is taken to be, the length of one instruction is taken to be 1 word long. Is there any problem in this concept?
No, ma'am.
So if I instead said that an instruction is packed in two words, then what would be the length of this instruction? It would have been
32 bits.
32 bits. 32.
yes. If I would have said it is packed in 4 words, then
64 bits.
64 bits.
64 bits.
but now since I'm not specifying anything, then it is taken to be the
16
normal word length, which is 16 bits. Okay. Now, what are the number of bits in the address part? So Nandini, please focus. This is one of the uh, doubts that you raised to me. Yes or no, Nandini?
Yes, ma'am.
Okay. So how to calculate this address part? I have done this with you earlier. Let me just look. I'll just share that PPT with you. Please, this is for everybody who is still facing a problem in this concept. Please look at it very carefully. I'll just share that other PPT with you. You can see the screen? Students,
Yes, ma'am.
Yes.
Okay. Okay. So, so you remember we had said that since this memory has 4096 words, okay, I can write it in the power of 2 as 2 raised to the power of 12. Is this clear or not? That 4096 words can be written as 2 raised to the power of 12 words.
Yes, ma'am.
Yes, ma'am. It's clear.
Any problem up till here?
No, ma'am.
No, ma'am.
No. So I had explained to you, I think, using a example earlier, that suppose I have suppose I have a Boolean variable x, okay, which has two values. Let's say we have a single Boolean variable x. Then how many values can it have?
Two.
Two values.
Two values, 0 and 1.
1. Yes. Suppose I have two Boolean variables x and y. Then what are the
4.
unique values that they can have?
4 values.
4.
0, 0.
0, 1.
0, 1.
1, 0. 1, 1.
If I have three Boolean variables,
8.
8 values.
8 values.
please speak up. These values.
8 values. 0, 0, 1. 0, 1.
Yes.
1,
1,
0, 0.
1. Next.
1, 0, 1.
1, 1, 0.
1, 1, 1.
Yes. And
1,
1,
1,
1, 1. Is this clear?
Yes, ma'am. Yes, ma'am.
Right. And so on, so forth. For four Boolean variables, let's say, okay, how many unique
16 values.
Boolean combinations will I have? 16. Okay. So when I had, in a sense, please see, So when I had one Boolean variable, how many unique possible combinations could I have? 2? Yes or no?
Yes, ma'am.
Yes, ma'am.
When I had 2 variables, how many unique combinations?
4,
Yes, ma'am.
3 variables,
8,
4 variables,
16,
16.
for 5 variables, this will be
32.
32 and so on, so forth. Is this clear? So
Yes, ma'am.
what is this 2 actually? Can I look at it as 2 raised to the power of 1?
1.
Yes or no, students?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, this is 2 raised to the power of 1. Now, in the second case, 4 is nothing but actually 2 raised to the power of
2.
I'm repeating this, giving it a lot of time because this is a very important concept. This is also a kind of numerical. There are a lot of numericals which are based on this concept. So I want you to understand them very carefully. So although I have done it, I think 2-3 times in the class earlier, but I'm still repeating it for you. So this is not just for Nandini, please. This is for anybody who's facing a problem here. Please look at these concepts once and for all, okay, and understand these basic concepts. They are very important. We are going to use them at many places. Okay, so 8 can be written as 2 raised to the power of 3, 16 can be written as 2 raised to the power of 4, 32 can be written as 2 raised to the power of 5. So can I generalize and say that in general, when I have n variables, yes, then I can have how many unique combinations?
2 raised to the power n.
2 raised to power n.
2 raised to the power of n, and vice versa. That is, if I had two unique combinations, 0 and 1, how many bits do I require to represent these 2 unique combinations?
1.
1. Similarly, when I had 4 unique combinations, how many variables did I require, or how many bits did I require? Only
2.
2. So please visualize that. Suppose we had a memory which only had 2 locations. Okay. Instead of this 4096 words that you see here, suppose my memory had only 2 locations. Okay. Then how many address bits would I have required? I would only have required 1 bit.
1 bit.
Yes. So it could either be a 0 or a 1, and we could access both the memory locations. Any problem?
No, ma'am.
Clear to everybody? Is there a single child to whom this concept is not clear? Is this point clear to everybody?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Sorry, come again. Come again. Who was this? Okay, so next time, when I suppose my memory has only 4 locations, then how many bits do I require to address these 4 locations?
2 bits.
Only 2 bits. Once these address bits could be 00, the next time they can be 01, the other time they can be 10, and yet another time they can be 11, and we will be able to access all 4 memory locations. Is this clear?
Yes, ma'am.
Yes, ma'am.
So in general, when I have 2 raised to the power of n memory locations, then how many address bits do I require?
Yes, ma'am.
N.
N.
N. Yes. So let me just come back to our original presentation now that we were discussing. Can you see the screen? Is
No,
the
ma'am.
screen
No,
visible?
ma'am.
Okay. Just give me. Is it visible now?
No, ma'am. Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay, okay. So how many bits will be required in this case for the address part? How many
12
address
bits.
bits will be required?
12 bits.
Since 4096 is equal to 2 raised to the power of 12, so how many bits? It would be 12 bits. Any problem?
No, ma'am.
No, ma'am.
No.
Okay. Now, let us say that we are only reserving 1 bit for the mode part. Okay. Then, how many bits will be left for the opcode part?
11.
Out of the 16 bits,
Three.
we have already, see, out of the 16 bits, we have already given 1 bit to the
Mode.
mode part, yes. Okay. And we have already seen that we require 12 bits for the address part. So how many bits are going to be
4.
left over for the opcode part now? Out of the 16, 12,
3.
3
bits.
minus 13 is
3
equal to
bits.
3 bits. Yes or no, students? Is this
Yes,
clear?
ma'am.
Yes, ma'am.
Yes, ma'am.
Good. And so how many operations are going to be possible with this kind of a instruction format?
8.
8.
How many operations will I be able to specify? Number of operations two raised to the power of 3, which is 8.
8.
Any problem? Any problem up
No,
till
ma'am.
now? Is it absolutely clear? Because this is the kind of, this is a very frequent kind of question that is asked to you both in the practicals, in Viva, and in the theory exams as well. Okay? Is this clear to everybody now?
Yes,
Yes,
ma'am.
ma'am.
Good. Let us move on to another example. So this is an example that this is a question that I've taken from your textbook. So I thought we could solve it in the class. So please see, a computer uses a memory unit with 256K words of 32 bits each. Okay, so now our memory unit looks like what? Let's just draw it so that we become a bit clearer. Okay, so this is something like this. Two 56A cross 32 bits. Yes or no?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay. Right. Now, a binary instruction code is used in one word of the memory. Okay. So this means that one instruction is equal to one word. Okay. And what is the word length here?
32 bits.
32.
32 bits.
Yes, it is 32 bits. Let me draw the instruction as well here for you. So one word is equal to, we note that. Mhm. So one word is equal to 32 bits. So what would be the length of the instruction?
32 bits.
32 bits.
The instruction has 4 parts. The instruction has 4 parts. Let's just draw these side by side. This is exactly the kind of question which is asked to you every year. So I thought I'll just take it up in the class. Okay. So it has 4 parts: an indirect bit, which is the mode bit. Okay, which is the mode bit. Now please see that they are saying that it is the indirect bit. Yes or no? So indirect bit means they have dedicated only one bit to the mode part. Okay. How many bits here? One bit for the mode part. Are you able to see all this
Yes, ma'am.
ma'am.
clearly? I'll just change the color of the text so that I think it will be more visible for you. Okay. So the next part is an opcode. It is an operation. So the instruction has 4 parts. One is the indirect bit, other is the opcode. Okay. Let's just draw this as well here. So this is the opcode. Okay. A register code. Now, what is a register code? See, we have seen that the basic computer uses how many registers?
8.
8.
It uses 8 registers. So, if we want to perform a operation with one of the registers, then we need to specify with which register we want to perform the operation. Clear? So that code which will point to a particular register, that means its name basically will be known as the register code. Is this clear or not?
Yes,
Yes,
ma'am.
ma'am.
And the fourth part is, he's saying a register code to specify one of the 64 registers. Okay, so as he told us, first of all, how many bits for the opcode as of now?
1 bit.
For the opcode beta. Not up till now. He has not told us any information that tells us this. Okay, but for the register code, he's telling us that the register code specifies 1 out of 64 registers. Okay, so 64 registers means 64 is 2 raised to the power of
6.
6. So how many bits will I require in this part?
6 bits.
6 bits. Okay, so I can work this out here. And the final part is the address part. Okay, the final part is the address part.
Excuse me, ma'am.
Yes.
Ma'am, indirect bit is mode.
Yes, the indirect bit is also known as the mode bit. Yes. I will tell you why. In some time I'll tell you why. Okay. So this is it, right? And he's saying up till now he's saying nothing about the address part. But can we calculate how many bits will be there in the address part? Who will answer this question? Let us see. Let me ask you.
Yes, ma'am. Using
Anchal Kashyap. Can you please switch on your video? Can you answer this question, beta? Okay. Sejal Mansoori. Yeah, tell me.
Ma'am, 16. 16.
How many? Sorry.
Ma'am, 16.
Okay. How did you work out 16?
Ma'am,
Please,
it's known.
everybody try and work out how many bits will be required for the address.
32. Ma'am, 8.
ma'am, 8.
Ma'am, 8.
Ma'am, 8.
8.
No, it's not 8.
32.
Ma'am, 11.
11.
No,
Yes.
it's not 11.
Ma'am, 12.
14, ma'am.
No.
8K.
Huh? Yes?
32.
32. No.
Is it 12?
No. Please speak up your name first and then
8K.
answer.
Ma'am, 24.
No. Let us see who can work this out today. I have done this so many times with you students. There is a little twist here.
Ma'am, 8K.
Okay, nobody? Nobody? Should I explain?
Ma'am, what exactly is K here?
K is
K
1000.
means 1000 words. K means 1000. Okay. So, as in your normal mathematical lingo, where you use K for kg. So, 1 kg is equal to 1000 grams, right? So, it is generally used for a kilo. 1000. Okay. So, although in computer science, 1K is equal to 1 kilobyte. Let me just tell you. Okay. Let me just tell you. Okay. So 1 KB is equal to 1024 bytes. Okay. Now, what is this? This is 1 kilo. This is also known as 1 kilobyte. It is also known as 1 kilobyte. Referred symbolically, it is displayed as capital K, capital B. Okay, it is equal to 1024 bytes. Now, if I write 1 kilobits, this is what? This is 1 kilo bits. This would be equal to 1024 bits. Okay, so in general, 1 K is taken to be 1000. Okay, it is presumed to be 1000. And 10254 is equal to how much? It is equal to 2 raised to the power of
10.
10. It is equal to 2 raised to the power of 10. Okay. Okay. So now when I work my example, coming back to the example now. So how many words do we have in this case now? In our case, this time, how many memory locations are there? 256K.
Okay.
So 256K means 256 is what? 256 is 2 raised to the power of 8.
8.
Right? And what is 1K equal to? It is
2 raised to the power
2 raised to
10.
the power of 10. We've just seen that. Is this clear up till now?
Yes, ma'am.
Yes.
So what will this be equal to?
2 raised to the power 18.
Power
Raised to
18.
the power 18.
When the bases are same, the powers are
Add.
Added.
added. So what do I get? Yes?
Yes, ma'am.
So how many bits will be required for the address bits?
18 bit.
18 bits.
18 bits will be required for the address part. Is this clear? This is how we calculate.
Yes,
Any
ma'am.
problem?
No, ma'am.
Right? Is this clear now? Anybody
Yes,
who is not clear with this? Okay. Okay. So the first part says how many bits are there in the operation code, the register code part and the address part. So we have calculated that apart from the operation code part. So now we can compute the operation code part. Please
7
calculate.
bits.
Ma'am, 7 bit.
Ma'am, it's 7 bits.
Just give me a minute, okay? Just give me a minute, Betty. So students, how many bits did you get?
7.
7.
7. Yes. Okay. How did we get this? Because the total length is 32 bits, right? And 32 bits minus 18 plus 6 is 24 plus 1 is 25. 32 minus 25 is 7 bits. Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
Any problem to anybody?
No, ma'am.
Excuse me, ma'am.
Yes. Who's this?
Can you repeat it?
Sorry, I can't hear you, Vita. Can you be a little
Can you
louder?
repeat it again?
I can't hear you. I can't hear you. Yeah, tell me. Yeah.
Ma'am, she's asking to repeat it.
Can you just type it in the chat box? I'm not able to hear you.
Ma'am, she's telling that please repeat that.
Okay, I'll do it on the screen and tell you. So we have to find this out, right? So what is the total number of bits in the complete instruction? 32. Please respond.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
What is the total number of bits that we have already dedicated? 1 to the mode bit? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Plus 6 to the registers
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
makes it 7. 1
Hmm.
plus 6 is equal to
7.
7.
7, sorry.
plus
18.
18 bits to the address part, which makes it equal to how many bits?
25.
25.
25 bits, right? So we have a total of 32 bits, and we have already dedicated 25 bits. Yes. So how many bits are we left?
7 bits.
The number of bits for the which are left for the opcode are
7.
okay, students. Is this clear now?
Yes, ma'am.
Yes, ma'am.
Yes,
Is there
ma'am.
a single student to whom? Yes. Yes. Somebody wants to ask me something? Okay. So I'll take it that this is clear to everybody now. I'll move on to the next part of the question. So the next part of the question says draw the instruction format and indicate the number of bits in each part. So we have already done that. You can see that on the screen. We have already done that. Is there any problem here?
No, ma'am.
No, ma'am.
Okay. Next is how many bits are there in the data and address inputs of the memory. Okay. How many bits are there in the data and address inputs of the memory? Anybody who would like to tell me what is meant by this question? Please say the question is very clear. We've just discussed this. Okay.
Ma'am, that how many total number of bits we are
Yes.
having?
Yes. How many bits are there in the data input of the memory? Means how many bits of data can I put in this memory or I can access from this memory? How many bits? We've just
32 bits.
one word is equal to 32 bits. So it would be 32 bits, right? And what about the address?
18
We
bits.
just
18 bits.
found out 18 bits. Is this clear?
Yes, ma'am.
Yes,
Okay.
ma'am.
So the solution to this example is already worked out on this slide as well. You can use this as a ready reference. Okay. Now I'm coming down to the next concept, which is the different types of instructions. So I'll be taking up this concept in the next class. This is going to be a very important class. Next class in this succession will be a very important class where we will be talking about the types of instructions. Okay, the different types of instructions. And this will then determine a lot of things. We will be talking about the instruction cycle. We will be talking about the interrupt cycle. All that will be based upon the next class. So I am just putting an end to our class today. And I want you to go through. I've been extremely patient and very slow working through these examples because these set the very basic for our future classes. So students, I would request you to go through these examples and work them with your own hand in the evening and let me know if you have a problem. in the next class, so that we are very clear about these basics when we take our journey forward. There was another question before I close. I'll take up. Let me first send the link of attendance for batch B1.
Ma'am,
And yes,
ma'am, please explain once this how we get this number of bits in register code 6.
but how many registers are given,
64.
which is equal to 2 raised to the power of?
6. Acha,
So
okay.
how many bits will be required to specify
6.
the? Yes. Is this clear
Okay.
now?
Yes, ma'am.
Okay, good. So there is another question that I think Nandini asked me. I'll take up your question in a minute, Nandini. The other
Ma'am,
question
I
that you
understood
want.
that.
Sorry, come again.
Understood that. The accumulator one, I got it.
I can't hear you, beta. I can't hear you. Can you just write it down in the chat, please? You've understood that. Okay, okay. No other problems, Nandini?
Ma'am, I had one problem in this one. Can you hear me?
You can just write it down in the chat, please. Can you please write it down in the chat? Okay, good, good. I'm just sharing the link for attendance today. Please mark your attendance and leave batch one, B1. The other people can leave. Okay. Thank you. Okay, Nandini has another question that she's asking me. She's saying that, ma'am, it is given that we need to specify one register out of 64 registers. Then shouldn't we use memory for one register only? Beta, at one time you are using one register. Maybe sometimes you use more than one register, but as you saw, we've made it very clear through the common bus system and the registers that I introduced to you in the basic computer, that all registers have their own individual functions. Okay, Nandini? Every register has its own specific function. Okay?
Yes, ma'am.
Okay.